welcome back. I'm glad you've returned to the silence. We leave the familiar behind to witness the silent beauty of the cosmos as we begin our long, drifting journey toward Uranus, the enigmatic ice giant that spins gracefully on its side in the outermost reaches of our solar system. This distant world challenges our fundamental understanding of planetary behavior, resting completely on its side as it completes its lonely 84-year journey around the sun. As we approach this pale turquoise sphere, the chaotic noise of our home planet fades into a distant memory, replaced by the profound, comforting stillness of the deep cosmic dark. Here, billions of miles away from the warmth of the inner planets, sunlight is reduced to nothing more than a brilliant star, casting a faint, cold glow upon a world wrapped in mystery. We are poised to explore a kingdom of extreme frost, where seasons stretch across decades and immense storms rage undetected beneath a deceptively calm exterior. Let us allow our consciousness to drift into this quiet realm, observing the subtle features of a planet that chooses to move to its own unique rhythm. To gaze upon this planet is to contemplate an ancient cosmic puzzle that planetary scientists have spent generations trying to decode. Unlike the other worlds in our stellar neighborhood, which spin like upright tops upon the fabric of space, this giant rolls along its orbital path like a perfectly smooth marble. We often ponder the incredible forces required to tip an entire world so completely, tilting its axis by 98 degrees and leaving its poles pointing almost directly at the sun. This remarkable posture means that for nearly half a lifetime, one pole is bathed in continuous, pale sunlight, while the opposite hemisphere is cast into a freezing darkness that lasts for 42 years. The atmosphere itself is a masterpiece of planetary chemistry, dominated by hydrogen and helium, but deeply enriched with methane gas that absorbs the red wavelengths of light. This selective absorption is the precise reason the planet greets us with its signature, serene aquamarine hue, a beautiful visual manifestation of cold molecules interacting with distant starlight. Beneath this smooth, featureless facade lies a surprisingly dynamic environment where winds can reach hundreds of miles per hour, silently carving the upper atmosphere without a single sound escaping into the void. As we float closer, we begin to perceive the intricate details that make this ice giant far more than a simple ball of frozen gas. It is a highly complex system, surrounded by a collection of faint, dark rings and a family of diverse moons, each holding its own secrets within the freezing space. Scientists rely on rare data from historic flybys and modern space telescopes to pierce the thick layer of haze that blankets the planet, revealing fascinating clues about its hidden interior. Unlike Jupiter and Saturn, which are massive balls of liquid hydrogen, this world holds a dense, slushy mantle composed of water, ammonia, and methane ices, resting above a relatively small, rocky core. The pressure within this deep planetary mantle is so intense that carbon atoms may actually crystallize, creating a literal rain of diamonds falling through the dark, liquid depths. Understanding this world requires us to reevaluate our definitions of planetary development, looking past the quiet exterior to appreciate the hidden mechanisms of the cosmos. Over the course of our exploration, we will uncover 100 distinct truths about this tilted giant, slowly peeling back the layers of methane, ice, and deep time. For now, we simply watch as the pale blue orb grows larger in our field of vision, inviting us to lose ourselves in its endless, quiet rotation. Stepping deeper into the vast atmospheric ocean of this distant giant, we discover an envelope of gas that is profoundly different from the air of the inner rocky worlds. The atmosphere is primarily composed of elemental hydrogen and helium, the ancient primordial gases that filled the early universe long before planets were born. Mixed into this light celestial blend is a small but incredibly influential percentage of methane gas, which acts as the defining characteristic of the planet's outer layers. These elements are tightly bound by gravity, wrapping the entire world in a thick, protective blanket that has remained largely undisturbed for billions of years. As we observe this delicate chemical balance, we begin to realize how a tiny shift in composition can fundamentally transform the nature of an entire planet, setting it completely apart from its giant neighbors. The presence of methane in the upper atmosphere plays a beautiful and dramatic role in determining how the planet appears to human eyes across the void of space. When the faint rays of sunlight finally complete their long journey to the ice giant, they penetrate deep into these upper gas layers before being reflected back out. The methane molecules act as a natural celestial filter, greedily absorbing the red portions of the light spectrum while allowing the blue and green wavelengths to pass through unhindered. This selective filtering creates the serene, uniform aquamarine hue that defines our visual experience of this lonely world. It is a striking reminder of how light and matter dance together in the darkness, transforming simple chemical interactions into breathtaking cosmic art that we can appreciate from billions of miles away. As we descend mentally into these beautiful blue-green mists, we encounter a realm of temperature so incredibly low that it holds a unique record within our stellar system. This world possesses the absolute coldest planetary atmosphere of any planet orbiting our central star, with temperatures plunging to -224 degrees Celsius. At these unfathomable depths of frost, molecular motion slows down to a crawl, and gases that would be invisible on Earth condense into thick, swirling clouds of ice. The sheer intensity of this chill creates an environment where energy is a rare and precious commodity, forcing the atmosphere into a state of heavy, cold stability. Contemplating this frozen landscape, we can appreciate the ultimate stillness of a world that has been deeply preserved by the absolute absence of warmth. This extreme cold presents a fascinating scientific paradox that continues to puzzle astrophysics experts who study the thermodynamics of giant planets. Nearby Neptune is located much farther away from the Sun, yet it radiates significantly more internal heat into space than its slightly smaller sibling. Our sideways spinning giant appears to have lost almost all of its primordial heat, radiating barely any energy beyond what it absorbs from the distant, pale sun. Scientists frequently wonder whether the cataclysmic ancient impact that knocked the planet onto its side also allowed its internal warmth to escape completely into the void. This lack of internal energy means the planet behaves like a true cryogenic laboratory, operating under completely different physical rules than any other giant planet we have observed. The structure of this chilly atmosphere is organized into distinct, predictable layers, much like the delicate strata of a frozen ocean. The lowest layer, known as the troposphere, is the most chaotic and dense region, where the vast majority of the planet's cloud systems are born and recycled. Above this lies the calm, stable stratosphere, followed by the incredibly thin and extended thermosphere that blends gradually into the vacuum of space. Each of these zones experiences its own unique relationship with the faint solar wind and the planet's strange magnetic field, creating invisible boundaries that shape the behavior of drifting particles. Navigating through these silent cosmic levels gives us a profound sense of structure, revealing that even a world of fluid gas possesses a deep, geometric order. Within the churning depths of the troposphere, scientists have identified multiple distinct cloud decks composed of exotic, frozen chemical compounds. The uppermost clouds, which give the planet its smooth and unbothered appearance, are made of tiny crystals of pure methane ice suspended in the hydrogen gas. Deeper down, beneath this beautiful aquamarine veil, lies a darker and heavier layer composed primarily of hydrogen sulfide ice. This is the very same compound responsible for the distinct and sharp smell of sulfur on Earth, transformed here into a massive, planet-wide weather feature. This stark contrast between outward visual beauty and inward chemical harshness is a recurring theme in the outer solar system, showing that tranquility can hide surprising realities. Despite the utter lack of substantial internal heat to drive atmospheric motion, the winds on this ice giant move with astonishing and terrifying velocity. Strands of cloud are whipped along lines of latitude by currents that can reach speeds of up to 900 kilometers per hour. These immense winds blow predominantly in the direction of the planet's rapid rotation near the poles, while moving in a backward direction near the equator. Because the atmosphere lacks solid ground or mountain ranges to slow these currents down, they can blow continuously for centuries without ever losing their incredible momentum. The result is a silent, perpetual motion machine of moving gas, carving the face of the planet in total, unbroken silence. When the Voyager spacecraft flew past this distant world in the mid-1980s, its cameras revealed a surface that looked as smooth and featureless as a polished stone. This deceptive calmness led many to believe the planet was a quiet, dormant world completely devoid of the dramatic storm systems seen on Jupiter or Saturn. However, modern observations using powerful infrared space telescopes have revealed that this serenity is merely a clever illusion created by the thick upper haze. Deep beneath the uniform blue fog, massive storms the size of entire continents rage across the landscape, flashing with silent lightning and tearing through the dark. This realization teaches us that a lack of visible activity does not mean a lack of deep, internal life and movement within the cosmic dark. The sunlight that reaches the upper layers of this world is about 400 times fainter than the bright illumination we experience on a clear day on Earth. Yet, even this incredibly weak and diluted solar energy is potent enough to trigger complex chemical reactions within the methane clouds. The distant ultraviolet rays strike the methane molecules, breaking their atomic bonds and forcing them to recombine into heavier hydrocarbons. This continuous, slow-motion process creates a delicate photochemical smog that blankets the stratosphere, adding a subtle layer of complexity to the atmosphere. It is a beautiful demonstration of the sun's reaching power, proving that even across billions of kilometers of empty space, a star can still alter the chemistry of a giant world. This high-altitude solar smog is composed of trace amounts of ethane, acetylene, and other complex organic molecules that drift slowly through the cold air. These heavy compounds act like a very fine, invisible dust, gently settling downward through the atmospheric layers over vast stretches of time. As they descend into the warmer, high-pressure regions deeper inside the planet, they are eventually broken down and recycled back into basic methane gas. This elegant, planet-wide recycling loop ensures that the atmosphere maintains its delicate chemical equilibrium over billions of planetary years. Watching this silent, cyclical dance of molecules helps us appreciate the grand, slow-moving systems that keep the cosmos in a state of perfect, enduring balance. Stepping deeper into the vast atmospheric ocean of this distant giant, we discover an envelope of gas that is profoundly different from the air of the inner rocky worlds. The atmosphere is primarily composed of elemental hydrogen and helium, the ancient primordial gases that filled the early universe long before planets were born. Mixed into this light celestial blend is a small but incredibly influential percentage of methane gas, which acts as the defining characteristic of the planet's outer layers. These elements are tightly bound by gravity, wrapping the entire world in a thick, protective blanket that has remained largely undisturbed for billions of years. As we observe this delicate chemical balance, we begin to realize how a tiny shift in composition can fundamentally transform the nature of an entire planet, setting it completely apart from its giant neighbors. The presence of methane in the upper atmosphere plays a beautiful and dramatic role in determining how the planet appears to human eyes across the void of space. When the faint rays of sunlight finally complete their long journey to the ice giant, they penetrate deep into these upper gas layers before being reflected back out. The methane molecules act as a natural celestial filter, greedily absorbing the red portions of the light spectrum while allowing the blue and green wavelengths to pass through unhindered. This selective filtering creates the serene, uniform aquamarine hue that defines our visual experience of this lonely world. It is a striking reminder of how light and matter dance together in the darkness, transforming simple chemical interactions into breathtaking cosmic art that we can appreciate from billions of miles away. As we descend mentally into these beautiful blue-green mists, we encounter a realm of temperature so incredibly low that it holds a unique record within our stellar system. This world possesses the absolute coldest planetary atmosphere of any planet orbiting our central star, with temperatures plunging to -224 degrees Celsius. At these unfathomable depths of frost, molecular motion slows down to a crawl, and gases that would be invisible on Earth condense into thick, swirling clouds of ice. The sheer intensity of this chill creates an environment where energy is a rare and precious commodity, forcing the atmosphere into a state of heavy, cold stability. Contemplating this frozen landscape, we can appreciate the ultimate stillness of a world that has been deeply preserved by the absolute absence of warmth. This extreme cold presents a fascinating scientific paradox that continues to puzzle astrophysics experts who study the thermodynamics of giant planets. Nearby Neptune is located much farther away from the Sun, yet it radiates significantly more internal heat into space than its slightly smaller sibling. Our sideways spinning giant appears to have lost almost all of its primordial heat, radiating barely any energy beyond what it absorbs from the distant, pale sun. Scientists frequently wonder whether the cataclysmic ancient impact that knocked the planet onto its side also allowed its internal warmth to escape completely into the void. This lack of internal energy means the planet behaves like a true cryogenic laboratory, operating under completely different physical rules than any other giant planet we have observed. The structure of this chilly atmosphere is organized into distinct, predictable layers, much like the delicate strata of a frozen ocean. The lowest layer, known as the troposphere, is the most chaotic and dense region, where the vast majority of the planet's cloud systems are born and recycled. Above this lies the calm, stable stratosphere, followed by the incredibly thin and extended thermosphere that blends gradually into the vacuum of space. Each of these zones experiences its own unique relationship with the faint solar wind and the planet's strange magnetic field, creating invisible boundaries that shape the behavior of drifting particles. Navigating through these silent cosmic levels gives us a profound sense of structure, revealing that even a world of fluid gas possesses a deep, geometric order. Within the churning depths of the troposphere, scientists have identified multiple distinct cloud decks composed of exotic, frozen chemical compounds. The uppermost clouds, which give the planet its smooth and unbothered appearance, are made of tiny crystals of pure methane ice suspended in the hydrogen gas. Deeper down, beneath this beautiful aquamarine veil, lies a darker and heavier layer composed primarily of hydrogen sulfide ice. This is the very same compound responsible for the distinct and sharp smell of sulfur on Earth, transformed here into a massive, planet-wide weather feature. This stark contrast between outward visual beauty and inward chemical harshness is a recurring theme in the outer solar system, showing that tranquility can hide surprising realities. Despite the utter lack of substantial internal heat to drive atmospheric motion, the winds on this ice giant move with astonishing and terrifying velocity. Strands of cloud are whipped along lines of latitude by currents that can reach speeds of up to 900 kilometers per hour. These immense winds blow predominantly in the direction of the planet's rapid rotation near the poles, while moving in a backward direction near the equator. Because the atmosphere lacks solid ground or mountain ranges to slow these currents down, they can blow continuously for centuries without ever losing their incredible momentum. The result is a silent, perpetual motion machine of moving gas, carving the face of the planet in total, unbroken silence. When the Voyager spacecraft flew past this distant world in the mid-1980s, its cameras revealed a surface that looked as smooth and featureless as a polished stone. This deceptive calmness led many to believe the planet was a quiet, dormant world completely devoid of the dramatic storm systems seen on Jupiter or Saturn. However, modern observations using powerful infrared space telescopes have revealed that this serenity is merely a clever illusion created by the thick upper haze. Deep beneath the uniform blue fog, massive storms the size of entire continents rage across the landscape, flashing with silent lightning and tearing through the dark. This realization teaches us that a lack of visible activity does not mean a lack of deep, internal life and movement within the cosmic dark. The sunlight that reaches the upper layers of this world is about 400 times fainter than the bright illumination we experience on a clear day on Earth. Yet, even this incredibly weak and diluted solar energy is potent enough to trigger complex chemical reactions within the methane clouds. The distant ultraviolet rays strike the methane molecules, breaking their atomic bonds and forcing them to recombine into heavier hydrocarbons. This continuous, slow-motion process creates a delicate photochemical smog that blankets the stratosphere, adding a subtle layer of complexity to the atmosphere. It is a beautiful demonstration of the sun's reaching power, proving that even across billions of kilometers of empty space, a star can still alter the chemistry of a giant world. This high-altitude solar smog is composed of trace amounts of ethane, acetylene, and other complex organic molecules that drift slowly through the cold air. These heavy compounds act like a very fine, invisible dust, gently settling downward through the atmospheric layers over vast stretches of time. As they descend into the warmer, high-pressure regions deeper inside the planet, they are eventually broken down and recycled back into basic methane gas. This elegant, planet-wide recycling loop ensures that the atmosphere maintains its delicate chemical equilibrium over billions of planetary years. Watching this silent, cyclical dance of molecules helps us appreciate the grand, slow-moving systems that keep the cosmos in a state of perfect, enduring balance. Descending far below the thick, photochemically altered clouds of methane and hydrogen sulfide, we begin to appreciate why planetary scientists classify this world not as a standard gas giant, but as a distinct ice giant. While Jupiter and Saturn are colossi dominated almost entirely by light hydrogen and helium gas, this planet possesses a much heavier proportion of water, ammonia, and methane. These compounds are referred to as ices in astrophysics, representing volatile chemical substances with freezing points far above those of the lightest primordial gases. This composition reveals a unique evolutionary pathway in the outer solar nebula, where the ambient temperatures were low enough for these heavy substances to condense in massive quantities. As we look deeper into the blue fog, we are peering into a world whose very identity is defined by these dense, fluid mixtures, rather than a simple sphere of swirling gas. Beneath the outer gas envelope lies the most massive region of the planet, a vast and swirling planetary mantle that makes up the bulk of its total volume. This is not a conventional ocean of liquid water like those found on Earth, but a super-pressurized, incredibly hot fluid that scientists often describe as a slushy, icy mantle. The temperatures in this deep zone actually rise to thousands of degrees, yet the crushing gravitational pressure prevents the water and ammonia from boiling away into gas. Instead, they exist in a highly exotic state, forming an electrical powerhouse that churns in total darkness beneath the calm aquamarine sky. This immense, hidden ocean is a fluid labyrinth where traditional definitions of liquid and solid lose meaning, creating a state of matter that can only exist under the most extreme planetary conditions. Deep within this boiling planetary mantle, the physical laws governing water molecules undergo a spectacular transformation under the influence of immense gravitational pressure. At these crushing depths, water enters an exotic state known as superionic ice, where oxygen atoms lock into a solid crystalline grid, while hydrogen ions flow freely through the structure like a liquid. This means the substance simultaneously behaves like a solid rock and a highly conductive liquid metal, a phenomenon that cannot naturally exist anywhere on the surface of our home planet. This bizarre form of water is highly effective at conducting electricity, turning the entire interior of the ice giant into a massive generator of strange physical forces. It forces us to reconsider the nature of water itself, showing that deep within the cosmos, the most familiar substance can become entirely alien. As we journey even further down into the high-pressure heart of the planetary mantle, the extreme environment begins to act upon the abundant methane molecules in a marvelous way. The immense weight of the upper planet tears the methane apart, separating the hydrogen atoms from the underlying carbon atoms. Under these hyperpressurized conditions, the isolated carbon atoms are compressed together until they crystallize into pure, glistening diamonds. These newly formed gemstones slowly drift downward through the hot, slushy ocean like a silent, slow-motion rainstorm of precious crystals falling toward the core. It is an extraordinary vision of hidden cosmic wealth, occurring in complete dark and isolation, completely shielded from human eyes by thousands of kilometers of freezing gas. At the very center of this grand icy matrix lies the definitive heart of the planet, a dense and compact core composed primarily of silicate rock and iron-nickel alloy. This central nucleus is roughly similar in mass to our entire home planet, yet it is compressed by the weight of the giant mantle into a relatively small, highly concentrated sphere. The pressures at this ultimate depth are unimaginable, anchoring the entire gravitational field of the ice giant and keeping its massive atmosphere bound to its side. Unlike the rocky worlds of the inner solar system, this core will never feel the touch of sunlight or interact directly with open space, remaining forever buried beneath thousands of miles of alien ocean. It serves as the solid anchor for the entire planetary system, a hidden foundation upon which the beautiful aquamarine world is built. One of the most profound realizations for any traveler exploring this distant world is the absolute absence of a well-defined solid surface anywhere on the planet. If an explorer were to descend through the atmosphere, they would notice the gas simply growing thicker and more dense, transitioning smoothly into a fluid state without ever hitting a distinct shoreline. There is no solid ground to stand upon, no mountains to climb, and no deep valleys to map. Only a seamless continuum stretching from space to the central core. This fluid nature creates a world of total fluidity, where the boundaries between the sky and the interior ocean are entirely blurred into a single grand system. It challenges our terrestrial instinct to look for solid ground, reminding us that the vast majority of matter in the outer solar system exists in a state of endless flow. Despite its large physical size and majestic appearance, this ice giant is actually the least massive of all the giant planets in our solar system. Its total mass is roughly 14.5 times that of the Earth, a substantial weight that nonetheless pales in comparison to the immense mass of nearby Neptune or the staggering weight of Jupiter. This relatively low mass suggests that during the early days of planetary formation, the world was unable to capture as much hydrogen and helium gas from the surrounding solar nebula as its larger siblings. It represents a delicate middle ground in cosmic architecture, a world that grew far larger than the inner rocky planets, but remained light and agile compared to the true gas colossi. This specific mass dictates everything about its gravity, its orbital dynamics, and the way it interacts with its surrounding family of moons. While its mass is relatively modest among the outer giants, its physical volume is still immense, capable of holding more than 63 Earths entirely inside its blue-green sphere. This combination of a large volume and a comparatively low mass means the planet has a very low overall density, ranking as the second least dense planet in our solar system, just behind Saturn. The planet is mostly composed of light elements and compressed fluids rather than heavy metals, giving it a soft and buoyant structural profile. If there were an ocean large enough to hold it, this giant would not sink easily, a testament to the ethereal and fluid substances that make up its colossal frame. This low density influences the planet's gravitational pull, creating a surprisingly gentle environment for a world of such grand proportions. Because the planet's low density offsets its massive volume, the gravity a person would experience at the top of its clouds is remarkably close to the gravity we feel on Earth. If one could somehow stand upon the upper cloud deck, they would experience a downward pull that is only about 86% of our familiar home gravity. This means a human traveler would actually feel slightly lighter on this giant world than they do while walking on the solid ground of their native planet. It is a stunning cosmic coincidence that a world so vastly different in scale and composition could mimic the gravitational comfort of our small terrestrial home so closely. This gentle pull shapes the behavior of the upper atmosphere, allowing the high-altitude mists to drift and churn without being violently crushed downward by a tyrannical gravitational field. The combination of this gentle gravity, fluid composition, and its rapid 17-hour rotation causes the planet to take on a highly distinct, flattened shape known as an oblate spheroid. As the world spins quickly around its tilted axis, the centrifugal forces push the material at its equator outward while flattening the regions around its lonely poles. This flattening is quite pronounced, making the equatorial diameter significantly wider than the distance measured from pole to pole across the center. When viewed through precise astronomical instruments, the planet is clearly not a perfect geometric circle, but a softly compressed oval drifting through the dark void. This distorted shape is a visible signature of the planet's internal kinetic energy, showing how speed and fluidity combine to reshape the geometry of a giant world. When the Voyager 2 spacecraft made its historic flyby in the mid-1980s, scientists were eagerly anticipating their first close look at the planet's invisible magnetic environment. Up until that definitive moment, humanity had assumed that all planets possessed magnetic fields roughly aligned with their axes of rotation, much like Earth or Jupiter. Instead, the data streaming back across the void revealed a magnetic structure that was completely chaotic and profoundly asymmetrical. This sudden revelation shattered existing models of planetary magnetism, proving that the outer solar system held entirely new rules of physics. It showed that the invisible energetic shield surrounding this pale blue world was just as unique and non-traditional as its dramatic sideways tilt. The most glaring abnormality discovered within this invisible shield is the astonishing angle at which the magnetic field lines emerge from the planet. The magnetic axis is tilted by nearly 60 degrees away from the planet's already highly unusual rotational axis. This means that while the planet rolls along its side through space, its magnetic poles are pointed in completely unexpected directions, almost out toward the equator. This radical misalignment creates a highly complex geometrical puzzle, where the lines of magnetic force are constantly twisted and warped by the planet's rapid 17-hour rotation. It stands as a striking departure from the magnetic harmony seen on other worlds, introducing a profound sense of asymmetry to the surrounding space environment. To make this magnetic puzzle even more intriguing, the center of the magnetic field does not originate from the rocky core at the planet's physical heart. Instead, the entire magnetic structure is offset from the center of the world by roughly 1/3 of the planet's total radius, shifted significantly toward the North Pole. This means the magnetic field is incredibly strong in some regions of the upper atmosphere, while being exceptionally weak on the opposite side of the planet. An explorer floating through the aquamarine clouds would experience a magnetic environment that changes drastically depending on their exact position over the landscape. This profound eccentricity suggests that the forces generating the field are not concentrated deep down, but are active closer to the outer layers. Because the planet combines a rapid 17-hour spin with a severely tilted and offset magnetic axis, its magnetosphere undergoes a wildly chaotic motion as it moves through space. Instead of a stable, symmetrical shield deflecting interstellar particles, the planet's magnetic field tumbles and gyrates like a lopsided top. As the world rolls along its 84-year orbit, this invisible bubble carves a complex, corkscrew path through the streaming solar wind. This constant twisting motion means the planet's space environment is in a perpetual state of transition, never settling into a steady equilibrium. Watching this invisible, energetic dance from afar reveals a world that interacts with the broader cosmos in a beautifully dynamic, almost living way. This bizarre magnetic asymmetry is direct evidence of the unusual mechanisms operating deep within the planet's slushy, high-pressure mantle. In traditional worlds like Earth, the magnetic field is generated by the churning action of molten iron within a deep, concentrated central core. On this ice giant, however, the field is believed to be produced by convective currents moving through the vast, superionic ocean of water and ammonia described earlier. Because this electrically conductive liquid layer sits far above the rocky core, the resulting magnetic forces are born in a wide, fluid zone rather than a single central point. This unique internal dynamo explains the field's strange offset and tilt, showing how the planet's fluid chemistry dictates its invisible influence on space. The chaotic tumbling of this lopsided magnetosphere creates a highly unusual relationship with the continuous stream of charged particles flowing outward from our Sun. As the magnetic shield rotates through the solar wind, it effectively opens and closes like a giant celestial valve every few hours. At certain points in the planet's rapid day, the magnetic lines connect smoothly with the solar wind, allowing energetic solar particles to slide deep into the atmosphere. A few hours later, as the planet continues its lopsided spin, the shield twists into a position that completely blocks and deflects the incoming solar stream. This rhythmic opening and closing creates a highly dynamic space weather system, where the planet is alternately exposed to and shielded from the cosmic elements. This highly irregular magnetic architecture produces planetary auroras that are profoundly different from the elegant, symmetrical light displays seen near the poles of Earth. Because the magnetic poles are highly tilted and offset, these celestial light shows do not gather in neat circles around the physical poles of the ice giant. Instead, the auroras flash in unexpected patches across the planet, appearing closer to the equator and shifting locations as the world tumbles through the dark. These invisible glow zones, captured by powerful space telescopes, appear as faint, fleeting bursts of ultraviolet light dancing silently above the aquamarine haze. They serve as a brilliant visual confirmation of the invisible geometric chaos reigning beneath the peaceful exterior of the upper clouds. Extending far behind the planet into the cold outer void is an immense magnetic tail, formed as the solar wind drags the lopsided magnetosphere downstream. Because the planet is rolling on its side while its magnetic field tumbles wildly, this magnetotail is twisted into a long, dramatic corkscrew shape, stretching across millions of kilometers. Trapped within this spiral tail are plasma particles and cosmic dust, spinning in a slow, hypnotic rhythm that mirrors the planet's own rotation. This elongated structure acts like a grand, energetic wake left behind by the ice giant as it completes its lonely 84-year journey around the sun. It highlights the vast reach of the planet's invisible presence, carving a complex and elegant signature into the fabric of the outer solar system. Within the protective embrace of this tumbling magnetosphere lie distinct radiation belts, where charged particles are trapped and accelerated by the magnetic forces. Surprisingly, despite the planet's massive size and chaotic fields, these radiation zones are remarkably mild and benign compared to the intense, deadly environment surrounding Jupiter. The presence of the planet's extensive ring system and its inner moons plays a vital role in cleaning up these energetic particles, acting like natural sponges that absorb radiation. As particles spiral along the tilted magnetic lines, they continuously collide with the orbiting rings and icy moons, neutralizing their dangerous energy. This creates a relatively peaceful space environment, proving that the planet's architectural features work together to maintain a gentle cosmic balance. The discovery and ongoing study of this bizarre, lopsided magnetosphere continues to challenge the fundamental boundaries of modern planetary science and dynamo theory. For generations, models of magnetic field generation were built upon the neat, symmetrical examples provided by the inner rocky worlds and the massive gas giants. This sideways spinning giant forced scientists to completely rethink how magnetic fields can behave, proving that nature can sustain highly irregular, stable dynamos across billions of years. It invites us to realize that our understanding of planetary physics is still evolving, with each distant world offering a new chapter in the grand book of the cosmos. As we contemplate this invisible, tumbling shield, we are reminded of the rich complexity hidden within the silent, icy depths of the outer solar system. Beyond the tumbling magnetic field and deep beneath the lopsided magnetosphere, the planet holds a delicate and shadowy ring system that remained invisible to human eyes for nearly 2 centuries after its initial discovery. In the late 1970s, astronomers were observing a distant star as the ice giant passed directly in front of it, hoping to study the planet's outer atmosphere. To their utter amazement, the starlight blinked out several times before and after the planet itself blocked the star, revealing the presence of a series of narrow, hidden structures circling the world. This unexpected discovery proved that planetary rings were not unique to Saturn, expanding our understanding of how matter organizes itself in the outer reaches of the solar system. It demonstrated how the universe can reveal its most delicate features through the simple alignment of distant starlight and patient observation. Unlike the brilliant, icy tracks that encircle Saturn like a shining highway, the rings of this sideways giant are incredibly dark, narrow, and faint, making them look like charcoal pathways drawn against the black velvet of space. They are composed of some of the least reflective material found anywhere in our stellar neighborhood, reflecting only a tiny fraction of the already dim sunlight that reaches them. Scientists believe these structures are relatively young, possibly formed from the remnants of an ancient moon that was torn apart by the planet's relentless gravitational tides. The narrowness of these bands suggests that powerful, unseen forces are actively working to keep the particles tightly confined, preventing them from scattering into the void. Watching these dark tracks loop around the aquamarine world creates a profound sense of fragile, geometric elegance, existing in total isolation. When we examine the composition of these dark cosmic ribbons, we find that they are not made of fine, dusty ice particles like the rings of other giant worlds, but are composed of larger chunks of rock and frozen boulders. These dark objects can measure anywhere from a few centimeters to several meters across, tumbling slowly in their orbits around the tilted equator. The extreme darkness of the material is likely the result of millions of years of intense radiation processing, which alters the surface of the frozen carbon and methane compounds. This continuous bombardment by cosmic rays strips away lighter elements, leaving behind a rich, tar-like organic residue that absorbs light like velvet. This unique chemical processing tells a silent story of deep time and cosmic exposure, where the elements themselves are slowly transformed by the energetic environment of outer space. Among the intricate network of these dark structures, the widest and most massive band is known to astronomers as the Epsilon ring, a prominent feature that anchors the entire system. This particular ring is highly eccentric and variable in width, stretching and compressing as it completes its rapid journey around the planet's equator. It is primarily composed of large, ice-rich boulders that are tightly packed together, creating a denser barrier than any of the neighboring rings. Because it stands out as the most prominent component, it has provided scientists with vital clues about the gravitational mechanics that govern the entire system. Observing the ebb and flow of this massive ribbon helps us appreciate the delicate gravitational choreography required to maintain order within a ring of tumbling space rocks. The pristine, sharp edges of this prominent epsilon ring are maintained by a pair of tiny, dedicated guardian satellites that orbit just inside and outside its boundaries. These shepherd moons, known as Cordelia and Ophelia, exert a subtle but continuous gravitational influence on the countless boulders drifting between them. The inner moon accelerates particles that drift too close, pushing them back out into the center of the track, while the outer moon slows down escaping particles, nudging them back inward. This endless cosmic dance keeps the ring perfectly confined, preventing the material from dissolving into the vast emptiness of the surrounding space. It is a beautiful example of celestial harmony, where tiny, frozen worlds act as silent keepers of a grand geometric masterpiece. As space telescopes and visiting probes peered closer into the darkness, the total count of these delicate structures grew to include 13 distinct and well-defined rings. These rings are organized into three main categories based on their distance from the planet, their thickness, and the size of the particles that compose them. The inner group consists of 9 narrow, intensely dark bands that hug the upper atmosphere, followed by 2 slightly wider rings farther out. Finally, the outer system features 2 brightly colored, ethereal rings that were discovered much later by advanced space-based observatories. This complex, multi-layered architecture reveals that the planet's immediate space environment is highly organized, divided into distinct zones of matter and motion. The outermost ring of this complex system exhibits a striking characteristic that sets it completely apart from the dark, charcoal bands closer to the planet. Known as the Mu Ring, this faint, ethereal ribbon glows with a distinct, beautiful blue color when viewed through advanced infrared and optical telescopes. This blue hue is exceptionally rare in planetary ring systems, shared only with the outer rings of Saturn, and indicates that the ring is composed of incredibly fine, microscopic dust particles. These tiny particles are effective at scattering shorter wavelengths of light, creating a ghostly blue aura that drifts silently in the deep dark. Scientists have traced the origin of this dust to a tiny, battered moon named Mab that orbits directly within the ring, continuously shedding material as it is struck by cosmic debris. Just inside this ghostly blue ribbon lies another outer ring that displays a completely different color signature, glowing with a soft, distinct red hue. This contrast between a blue outer ring and a red inner ring represents a fascinating cosmic riddle, showing that 2 structures in close proximity can have entirely different histories and compositions. The red color suggests that this band is composed of larger particles or material that is heavily enriched with iron oxides or complex organic polymers. This sudden shift in color and particle size highlights the incredible diversity hidden within a single planetary system, where small changes in location result in completely different physical realities. It invites us to think about the complex sorting mechanisms of gravity, which can separate different types of cosmic dust into neat, color-coded tracks around a giant world. Closer to the planet's upper atmosphere, filling the spaces between the main narrow tracks, lies a collection of faint, diffuse sheets of dust that are barely perceptible against the dark void. These dusty bands are not made of solid boulders, but are instead composed of microscopic grains that are slowly spiraling inward toward the aquamarine clouds. This dust is continuously generated as the larger rocks in the main rings collide with each other and with incoming micrometeorites, creating a fine debris trail. over long stretches of time, atmospheric drag from the planet's extended upper layers slows these dust grains down, pulling them toward a silent demise in the methane mists below. This process represents a continuous, slow-motion leak of material, proving that even the most stable-looking cosmic structures are in a state of perpetual, evolutionary change. Despite stretching across tens of thousands of kilometers of space around the planet's equator, these rings are astonishingly thin, measuring only a few meters in vertical thickness. If an observer were to look at them edge-on from the plane of the equator, the entire magnificent system would completely disappear from view, becoming a razor-thin line of total invisibility. This extreme flatness is a direct consequence of countless collisions over billions of years, which have neutralized any upward or downward motion among the particles, forcing them into a single, perfectly flat geometric plane. It is a breathtaking realization that structures so incredibly wide can be so fragile and thin, maintaining their integrity across eons through the pure physics of rotation and gravity. As we watch these delicate, charcoal circles spin endlessly around the quiet aquamarine giant, we are struck by the perfect, unbothered order that governs even the darkest corners of our universe. Beyond the flat, charcoal pathways of the ring system, the ice giant commands a vast and diverse family of 27 known moons that orbit gracefully in the darkness. Because the planet itself rolls along its side through the cosmos, this entire satellite system is tilted at the very same dramatic angle, circling the equator like a vertical Ferris wheel. These moons move in near-perfect circular orbits, remaining strictly bound to the planet's unique orientation despite the intense gravitational disruptions of the outer solar system. This alignment suggests that the inner moons formed directly from the thick disk of debris left behind after the ancient, cataclysmic planetary collision. As we watch this collection of frozen worlds spin through the dark, we perceive a miniature solar system operating within its own sideways architecture. It represents a beautifully coordinated system of matter, tracking the planet's unorthodox posture with absolute orbital fidelity across billions of cosmic years. The naming convention of these orbiting companions sets them completely apart from any other satellite family in our stellar neighborhood. While the moons of Jupiter, Saturn, and Neptune are named after characters from classical Greek and Roman mythology, these worlds draw their identities from English literature. Astronomers chose to honor the timeless creations of William Shakespeare and Alexander Pope, filling the icy void with names like Titania, Oberon, Ariel, and Miranda. This poetic choice infuses the cold, remote system with a profound sense of human artistry and dramatic history, linking the outer cosmos to our cultural heritage. Each moon carries the spirit of a literary character, transforming the silent space around the aquamarine giant into a theater of frozen celestial bodies. It stands as a beautiful testament to humanity's desire to project its own storytelling traditions onto the blank canvas of the deep cosmic night. To better understand the complex dynamics of this satellite family, planetary scientists divide the 27 companions into 3 distinct structural groups. The first group consists of 13 small inner satellites that are intimately linked with the dark ring system, acting as gravitational anchors in the upper atmosphere. Beyond these narrow pathways lie the 5 massive major moons, which represent the true heavyweights of the planetary system and hold the vast majority of its satellite mass. Finally, a loose collection of 9 irregular outer moons orbits at immense distances, moving along highly eccentric and tilted tracks far into the interstellar void. This 3-tiered architecture demonstrates how gravity can sort matter into distinct zones of influence, creating a highly organized planetary kingdom out of ancient space debris. It allows us to view the system as a complex, multi-layered matrix, where each group plays a specific role in maintaining global equilibrium. The true highlights of this distant planetary system are the 5 major satellites, a collection of substantial worlds that deserve close scientific contemplation. These 5 celestial bodies, ranging from the fractured terrain of Miranda to the ancient highlands of Oberon, are large enough to have achieved hydrostatic equilibrium, shaping themselves into smooth spheres under their own gravity. They are primarily composed of roughly equal mixtures of water ice and silicate rock, creating frozen landscapes that hide complex geological histories beneath their icy crusts. Unlike the completely gas-dominated environment of their parent planet, these moons offer solid surfaces where craters, valleys, and immense cliffs can permanently preserve the scars of deep time. Exploring these major satellites allows us to transition from the fluid dynamics of the gas layers to the rigid, enduring realities of frozen planetary geology. They stand as silent sentinels, each holding a unique chapter of the system's ancient evolution written into their frozen topography. The undisputed queen of this satellite family is Titania, the largest and most massive moon orbiting the sideways spinning ice giant. Stretching across a diameter of more than 1,500 kilometers, this substantial world possesses a surface that tells a story of intense internal activity and structural transformation. The landscape is crisscrossed by an extensive network of massive fault valleys and giant scarps, proving that the moon experienced dramatic tectonic fracturing in its distant past. One of the most prominent features is a colossal canyon system that dwarfs the largest valleys on Earth, cutting a deep scar across the frozen hemisphere. This geological activity suggests that as the moon's internal water ocean froze billions of years ago, the expanding ice literally cracked the outer rocky crust from the inside out. Watching this grand, fractured world drift through space reminds us that even the coldest, most remote bodies can possess an energetic history capable of reshaping their entire geography. Orbiting at the farthest edge of the major satellite system lies Oberon, the second largest moon and a world frozen in a state of ancient, undisturbed preservation. Because it rests so far away from the gravitational disruptions of the parent planet, its surface has remained largely unbothered by internal geological activity for eons. Instead, the moon presents a heavily cratered landscape that serves as a permanent historical archive of the early, violent days of the solar system. Nearly every square kilometer of its icy crust is saturated with impact scars, many of which are surrounded by bright rays of fresh ice blasted out from the interior. Nestled within some of these ancient craters is a mysterious, dark material that scientists believe may have welled up from deep underground reservoirs long ago. This distant world acts as a silent time capsule, holding the pristine record of cosmic bombardment completely intact across billions of years of isolation. Moving inward toward the planet, we encounter Umbriel, a world that holds the title of the darkest and most mysterious of the 5 major moons. Its surface reflects only a tiny fraction of the faint sunlight that reaches it, covered in a uniform layer of dark, ancient ice that lacks the bright ray craters seen on its neighbors. This lack of visual contrast makes the moon look like a shadowy ghost drifting through the space environment, hiding its geological features from easy observation. However, this dark monotony is broken by a single, spectacular feature known as Wanda, a highly reflective ring of bright material sitting inside an equatorial crater. Scientists frequently debate the origin of this brilliant white feature, wondering if it represents a fresh deposit of pure carbon dioxide ice or a unique impact that exposed clean underground layers. This stark visual contrast creates an alluring cosmic riddle, a bright beacon of light shining out from a world wrapped in perpetual shadow. In complete contrast to its dark neighbor, the moon named Ariel stands out as the brightest and geologically youngest surface among all the major satellites. When space probes first captured images of this striking world, they revealed a landscape that was remarkably smooth and largely free of ancient impact craters. Instead, the surface is dominated by vast, interconnected valley networks and deeply carved troughs that look like grand planetary highways cutting through the ice. This lack of heavy cratering proves that the moon underwent a massive resurfacing event relatively recently in cosmic history, erasing its ancient past. Internal tidal heating, caused by gravitational tugs from neighboring moons, likely kept the interior warm enough to drive a unique form of ice volcanism. This process allowed soft, fluid mixtures of water and ammonia to well up onto the surface, smoothly paving over old scars and creating a pristine, reflective terrain. The closest and undoubtedly the strangest of the major satellites is Miranda, a tiny world that possesses some of the most chaotic and bizarre geology found anywhere in the known universe. Its surface looks like a giant, mismatched jigsaw puzzle, where completely different types of terrain are crammed together in an unnatural, fractured jumble. Massive, parallel ridges and deep grooves, known as coronae, sit directly adjacent to ancient, heavily cratered plains without any smooth transition. This chaotic architecture includes Verona Rupes, a staggering vertical cliff that stands as the tallest known drop in the solar system, plunging down several kilometers into the dark. For generations, scientists wondered if the moon had been completely shattered by a giant impact and then loosely reassembled by gravity into this scrambled form. Modern research suggests that intense, localized tidal forces caused sections of the crust to sink and churn, creating a beautiful monument to gravitational stress and structural chaos. The intricate movements of these 5 major worlds are governed by complex orbital resonances that keep the entire system stable over vast stretches of time. As they circle the tilted equator of the ice giant, their gravitational fields continuously interact, tugging on one another in a slow, rhythmic celestial dance. These subtle interactions prevent the moons from drifting out of their designated pathways, maintaining a perfect orbital harmony despite the planet's unorthodox orientation. Over millions of years, these gravitational relationships have shaped the internal temperatures of the moons, driving the geological activity and resurfacing events observed on their surfaces. It is a profound realization that within a system that appears so radically tilted and disrupted from the outside, internal stability is preserved through the elegant mathematics of gravity. We watch as these diverse icy worlds continue their silent, synchronized journey around the aquamarine giant, perfectly balanced within the dark envelope of outer space. As this tilted world moves slowly along its wide 84-year orbital path, the unique 98-degree orientation creates a seasonal climate that is entirely unparalleled in its extremity. During the height of the planetary solstice, one of the lonely poles points almost directly at the brilliant pinpoint of the distant sun, basking in continuous, unbroken twilight. Meanwhile, the opposite hemisphere is turned completely away from the solar rays, plunging into a freezing, starlit darkness that endures without interruption for more than 2 decades. This radical distribution of light means that the concept of a normal day and night completely ceases to exist across vast swathes of the planet for a quarter of its long year. Scientists marvel at how an atmosphere can endure such prolonged periods of complete exposure and total isolation. Watching the subtle shifts in cloud patterns as the light slowly creeps across the landscape, The sheer scale of this polar illumination shapes the deep energy balance of the entire upper atmosphere, locking the world into a slow, multi-decade meteorological rhythm. The profound stillness of the solstice gradually gives way as the planet drifts further along its track, eventually arriving at the beautiful period of the planetary equinox. During this brief astronomical transition, the sun rises directly over the equator, allowing the entire world to experience a rapid 17-hour cycle of day and night, just like the inner worlds. For a few short years, the rotating globe is illuminated from side to side, casting long shadows across the dark ring tracks and the vertical paths of the orbiting moons. This sudden change in solar orientation injects a fresh pulse of energy into the atmosphere, awakening dormant weather systems that were previously suppressed by the long polar night. It is a rare moment of symmetry for an otherwise lopsided world, a time when the forces of light and dark are distributed evenly across the vast aquamarine expanse. Astronomers on Earth track these equinox periods with intense fascination, knowing they offer a fleeting window into the planet's most active and dynamic atmospheric transformations. One might expect that the pole receiving continuous sunlight for decades would become the hottest region on the planet. Yet the physics of the atmosphere reveal a much more complex reality. The dense layers of hydrogen, helium, and methane possess an immense capacity for storing cold, creating a phenomenon known as deep thermal inertia. This means that the atmosphere responds incredibly slowly to the shifting rays of the distant sun, requiring years of continuous exposure before any significant change in temperature can be measured. The warmth received from the pinpoint star is so faint that it struggles to penetrate into the heavy cloud decks, leaving the deep troposphere largely unbothered by the changing seasons above. This creates a fascinating lag in the planetary climate, where the highest temperatures are often recorded long after the solstice has passed into history. It teaches us that in the outer solar system, time and temperature move in a slow, muted relationship that operates on a scale far beyond human experience. This slow thermal response contributes to one of the most baffling meteorological paradoxes discovered by modern planetary science. Despite one pole being bathed in continuous sunlight and the equator receiving far less total solar energy over the course of the year, observations show that the equator remains slightly warmer than the poles. Scientists have spent decades developing complex circulation models to explain how an unilluminated region can maintain a higher temperature than a sunlit one. The prevailing theory suggests that powerful global wind systems are highly efficient at redistributing what little energy exists, carrying warmth away from the poles and concentrating it around the planet's midsections. This constant, invisible transfer of heat keeps the planet in a state of global equilibrium, preventing the dark hemisphere from freezing completely solid while the sunlit side bakes in the pale light. It is a striking example of a planet working as a unified fluid system, using its immense internal dynamics to overcome the challenges of its extreme sideways posture. As the seasons slowly shift over the decades, the appearance of the upper atmosphere undergoes a visual transformation marked by the formation of vast polar hoods. These features appear as subtle, highly reflective caps of thick methane, haze that settle over whichever pole is currently transitioning into the long summer season. The continuous, low-energy ultraviolet light from the sun drives the photochemical reactions described earlier, causing complex hydrocarbons to gather and thicken above the polar regions. This brightening effect acts like a giant celestial mirror, reflecting a portion of the incoming sunlight back out into the void and further cooling the air below. When the pole finally begins to tilt away from the light, this protective hood slowly dissolves, allowing the underlying aquamarine clouds to become visible once again. Watching these ghostly hoods appear and vanish over the course of 84 Earth years allows us to witness the slow, deliberate breathing of a giant planetary climate system. The dramatic progression of the seasons also has a profound impact on how the planet's lopsided, tumbling magnetosphere interacts with the continuous stream of the solar wind. During the solstices, when the rotational axis points almost directly toward the sun, the twisted magnetic tail described earlier is aligned nearly parallel to the incoming solar stream. This creates a highly stable, streaming configuration where the solar wind slides smoothly along the corkscrew lines of magnetic force without causing massive disruptions. However, as the planet approaches the equinox and rolls sideways to the solar flow, the magnetosphere is subjected to a violent, buffeting action as it spins through the dark. The magnetic shield effectively slaps against the incoming particles every 17 hours, creating powerful ripples and fluctuations that echo across the entire space environment. This seasonal shift in magnetic geometry transforms the space surrounding the ice giant from a quiet, streaming highway into a highly turbulent arena of cosmic physics. Deep within the calm, stable layers of the stratosphere, scientists have detected subtle temperature inversions that are intimately linked to the planet's long-term seasonal cycles. Unlike the lower troposphere, which grows colder with altitude, these upper gas layers show a surprising increase in warmth as one travels higher toward the edge of space. This warming is caused by the trace amounts of ethane and acetylene smog absorbing the faint solar radiation and converting it directly into thermal energy. Over the course of the long decades, these warm zones shift slowly between the hemispheres, following the path of the sun across the tilted sky. This delicate thermal structure creates a series of invisible barriers that prevent the rapid mixing of gases between the different atmospheric levels, stabilizing the upper air. It reveals that even within a world defined by extreme cold, delicate pockets of relative warmth can exist, shaped by the interplay of organic chemistry and distant starlight. Operating as a true cryogenic laboratory in the deep dark, the planet must constantly balance the tiny amount of energy it receives with its own output of infrared radiation. Because the world lacks any significant internal heat source of its own, it behaves almost like a perfect cosmic mirror, radiating back into space exactly as much energy as it absorbs from the sun. This delicate radiative balance means the planet is locked in a state of perpetual thermal conservation, unable to generate the massive internal heat engines seen on Jupiter or Saturn. The infrared light emitted from the upper cloud decks is incredibly faint, traveling silently out into the interstellar void as a whisper of heat. Scientists study this cooling process to better understand how giant worlds lose their primordial energy over billions of years, using the planet as a baseline for the coldest possible planetary environments. It offers a vision of ultimate planetary efficiency, a world that has adapted perfectly to the extreme conditions of the outer solar system. The year 2007 marked a monumental milestone in the modern study of this ice giant, as the planet reached its highly anticipated equinox for the first time since the dawn of advanced digital astronomy. As the world aligned perfectly with Earth's orbit, astronomers were treated to the spectacular sight of the dark ring system being viewed completely edge-on, appearing as a razor-thin line cutting across the aquamarine disk. This unique perspective allowed scientists to observe the shadows of the rings, casting long, dark pathways across the cloud tops, revealing the subtle three-dimensional structure of the atmosphere. The sudden, even distribution of sunlight triggered a surge of new storm features and bright cloud bands that had never been documented before, shattering the old myth of a dormant planet. It proved that when given the right seasonal catalyst, this quiet giant can erupt into a display of atmospheric vitality that rivals any world in the cosmos. These historic observations provided a treasure trove of data, allowing us to reconstruct the complex meteorological history of a world that hides its secrets across decades of time. The ultimate driving force behind the planet's enduring climate is a grand system of global circulation that moves mass and energy across thousands of kilometers of fluid terrain. Because the world lacks solid continents or mountain ranges to disrupt the flow, these atmospheric currents organize themselves into massive, planet-wide corridors that wrap around the lines of latitude. Deep convective plumes rise slowly from the high-pressure depths of the mantle, carrying trace chemical compounds and subtle pulses of energy up to the cold upper sky. These rising currents are then captured by the rapid 900 km/h winds, which distribute the heat evenly across the flattened shape of the oblate spheroid. This highly efficient plumbing system ensures that despite the extreme sideways tilt and decades of localized darkness, the planet maintains a remarkably uniform global temperature profile. It is a beautiful manifestation of planetary harmony, a fluid engine that continuously works to smooth out the imbalances of the cosmos, allowing the ice giant to drift peacefully through the infinite dark. In the golden age of robotic space exploration, humanity sent a lone mechanical emissary to execute the only close-up survey of this distant aquamarine world. The Voyager 2 spacecraft launched from Earth in the late 1970s, embarking on a grand tour of the outer planets that would eventually bring it to the doorstep of the ice giant. By January of 1986, the silent probe reached its closest approach, skimming just 81,000 kilometers above the frozen cloud tops. This daring flyby captured thousands of highly detailed images and invaluable physical measurements, transforming our understanding of the planet from a fuzzy, distant dot into a rich and complex world. The data gathered during those few historic hours remains the primary foundational archive for modern scientists studying the planet's unique characteristics. It stands as a brilliant monument to human ingenuity, a testament to what can be achieved when a machine is cast into the deep dark to listen to the whispers of an alien giant. Operating a robotic spacecraft at such an immense distance from Earth presented an array of unprecedented technological and engineering hurdles for the mission control team. Because the sunlight reaching the planet is so incredibly faint, the spacecraft's cameras required much longer exposure times to capture clear images of the dark rings and cloud structures. To prevent the moving probe from blurring the photographs, engineers developed a highly precise technique called attitude control to smoothly pivot the spacecraft during each exposure. The weak radio signals carrying these precious images took nearly 3 hours to travel across the vast void back to human receivers, moving at the absolute speed of light. Every line of data received was a precious gift from the darkness, revealing a quiet world that had kept its features hidden from terrestrial eyes for centuries. This delicate orchestration of light and movement proved that humanity could successfully navigate the extreme limitations of the deep outer solar system. Following the historic departure of Voyager 2 into the interstellar void, the responsibility for monitoring the ice giant shifted back to advanced observatories positioned closer to home. The deployment of the Hubble Space Telescope in the early 1990s provided a revolutionary new eye in orbit, completely free from the distorting effects of Earth's heavy atmosphere. Equipped with highly sensitive digital sensors, this orbital observatory began capturing regular, high-resolution snapshots of the pale blue sphere across multiple decades. These ongoing observations allowed scientists to track the slow progression of the 20-year seasons, documenting the sudden emergence of bright cloud features as the planet approached its equinox. Hubble effectively bridged the massive gap in time between deep space missions, proving that a telescope orbiting our home planet can still unlock the mysteries of a world billions of kilometers away. While space-based telescopes offered pristine views, groundbreaking advancements in terrestrial engineering allowed giant ground-based observatories to pierce the veil of the outer solar system as well. Astronomers utilized massive telescopes equipped with sophisticated adaptive optics systems, which use lasers to measure and actively correct for the constant shimmering of Earth's atmosphere. By using powerful infrared detectors, these giant instruments could see right through the uniform blue methane haze that had looked so featureless to the passing Voyager probe. This technique revealed the hidden continent-sized storm systems, rapid wind currents, and delicate structural variations churning deep within the lower troposphere. It represents a beautiful triumph of human creativity, showing that, with the right technology, we can turn the blurry air of our native planet into a crystal-clear window, looking out at a frozen giant. The primary scientific tool used to decode the exact chemical recipe of this distant atmosphere is the elegant methodology of astronomical spectroscopy. By carefully spreading the reflected starlight from the planet into a highly detailed spectrum of colors, scientists can read the unique light fingerprints left behind by individual molecules. This precise analysis is how researchers detected the prominent presence of methane, hydrogen sulfide, and the high-altitude smog of ethane and acetylene described in earlier chapters. Every dark line crossing the colorful spectrum represents a specific wavelength of light absorbed by a gas molecule tumbling in the icy sky. It allows us to analyze the exact composition of a world without ever needing to touch its fluid atmosphere, turning the simple act of looking into a deep chemical exploration of the cosmos. Another remarkably clever technique used to measure the structural profile of the atmosphere involved using the spacecraft's radio transmitter as a cosmic probe. As Voyager 2 drifted behind the edge of the planet, its radio signals were forced to slice directly through the thick layers of gas before being completely blocked by the core. Scientists on Earth carefully measured how these radio waves were bent, slowed down, and absorbed by the different densities of hydrogen and helium. This radio occultation experiment provided a highly accurate temperature and pressure map of the troposphere, revealing the absolute cold of the upper clouds. It demonstrated how a simple communication signal can be repurposed into a powerful tool of discovery, peeling back the layers of an alien sky through the pure physics of wave propagation. Despite the immense success of these various observational techniques, our understanding of the ice giant remains deeply incomplete due to the sheer difficulty of sending a dedicated mission back to its orbit. Launching a modern spacecraft to this remote destination requires a journey that can last well over a decade, demanding a level of institutional patience that is rare in human endeavors. Because the solar energy at that distance is far too weak to power traditional solar panels, any future spacecraft must rely entirely on nuclear power sources like plutonium generators to keep its instruments alive. The intense cold of the outer void also requires sophisticated thermal shields and internal heaters to prevent the delicate electronics from freezing solid during the long transit. Overcoming these daunting challenges requires a grand commitment to scientific discovery, pushing the very boundaries of what our technology can achieve in the deep freeze of space. In recent years, the international scientific community has identified a dedicated mission to this sideways planet as one of the highest priorities for the future of space exploration. The proposed mission concept, known to researchers as the Uranus orbiter and probe, involves an advanced spacecraft designed to enter a permanent orbit around the ice giant, while dropping a small metallic capsule directly into its clouds. This atmospheric probe would descend slowly under a parachute, measuring the precise ratios of noble gases and chemical isotopes that have remained unchanged since the birth of the solar system. Meanwhile, the main orbiter would spend years weaving between the dark charcoal rings and the vertical orbits of the literary moons, mapping their geography with unprecedented clarity. Such a mission would provide the definitive answers to our questions about planetary formation, transforming our understanding of how ice giants develop across the galaxy. To successfully send a massive modern orbiter to the outer solar system without consuming an impossible amount of rocket fuel, navigation experts must utilize the elegant physics of gravity assists. A spacecraft launched from Earth will deliberately fly close to intermediate planets like Venus, Earth itself, or massive Jupiter, using their gravitational fields as cosmic slingshots. As the probe swings through the orbital wake of these worlds, it steals a tiny fraction of their orbital energy, accelerating dramatically without burning a single drop of onboard propellant. This complex orbital choreography requires calculations of absolute precision, aligning the launch window with the specific geometric placement of the planets across multiple years. It highlights the deeply interconnected nature of our solar system, where the movements of the inner rocky worlds are used to bridge the immense gulf separating us from the lopsided giant. The ongoing drive to explore and understand this distant world is fueled by a profound realization that ice giants are incredibly common throughout the broader universe. Data from modern planet-hunting space telescopes have revealed that worlds of similar mass and size to our aquamarine giant are among the most abundant types of planets orbiting other stars in the galaxy. By studying the lopsided magnetic field, the diamond rain, and the seasonal weather patterns of our local ice giant, scientists are effectively creating a master template to understand thousands of alien worlds across the cosmos. It transforms the planet from a lonely, eccentric anomaly in our own solar system into a vital gateway for understanding the architecture of the wider universe. Every secret we unlock within its frozen methane clouds brings us one step closer to comprehending the endless diversity of the infinite starry sky. Deep within the chemical signatures analyzed by our modern instruments, scientists have carefully measured the ratio of deuterium to normal hydrogen in the planet's fluid envelope. Deuterium, often called heavy hydrogen, contains an extra neutron and serves as an ancient chemical fingerprint from the dawn of creation. The specific abundance of this isotope on the ice giant is significantly higher than what we observe on the gas colossi Jupiter and Saturn, indicating a completely different birthplace in the early solar nebula. This chemical disparity suggests that the planet formed from material that condensed in much colder, more remote regions of space where heavy hydrogen could easily gather. By analyzing these subtle atomic variations, astrophysicists can effectively look back through billions of years of time, mapping the primal layout of our stellar system before the planets even settled into their current positions. When we compare this aquamarine world to its distant blue sibling, Neptune, we are confronted with a fascinating tale of planetary twins that diverged along separate evolutionary paths. Both worlds share remarkably similar sizes, masses, and deep structural layers, containing a slushy mantle of superionic water and ammonia resting above a dense rocky core. Yet, as noted during our consideration of planetary warmth, Neptune boasts a powerful internal heat engine that drives violent, expressive storm systems across its face, while our sideways giant remains quietly dormant. This stark difference in energetic behavior continues to inspire deep scientific inquiry, prompting researchers to question why one twin preserved its primordial heat while the other lost it entirely to the void. It serves as a beautiful reminder that in the cosmos, even worlds born from the exact same cosmic recipe can develop entirely unique personalities and physical realities. The immense gravitational reach of the lopsided giant extends far beyond its literary moons and dark charcoal rings, capturing a collection of faint, elusive companions known as Trojan asteroids. These ancient space rocks share the planet's wide 84-year orbital path. Hovering in stable gravitational pockets located 60 degrees ahead of and behind the planet in its journey around the sun. Because these objects move in perfect synchronization with the ice giant, they never collide with it, instead acting as a quiet celestial escort through the outer solar system. The discovery of these co-orbital bodies proves that even a world rolling along its side can maintain a highly stable, orderly environment across billions of kilometers of empty space. They represent the primal leftovers of planetary formation, preserved in the dark vacuum like silent spectators, tracking the slow, majestic roll of the aquamarine sphere. The delicate stratification of the planet's upper air reveals an environment that is remarkably clean and free from the heavy, complex chemical smog found on worlds closer to the sun. While Saturn and Jupiter are wrapped in thick, churning bands of ammonia gas and complex sulfur compounds, the extreme cold of our sideways giant forces these substances to freeze out completely at much deeper levels. As a result, the pristine stratosphere is dominated almost exclusively by pure hydrogen and helium, with only trace amounts of the light methane haze filtering up from below. This high-altitude clarity allows distant starlight and weak solar rays to penetrate deeper into the atmosphere before interacting with the molecular layers. It gives the upper atmosphere a unique, crystalline quality, an untainted cosmic window where the physics of light and gas operate in their simplest, most elegant forms. The continuous preservation of the 13 narrow ring tracks introduces a fascinating paradox regarding the ultimate lifespan and stability of structures in the outer solar system. Left entirely to themselves, the dark charcoal boulders and icy rocks would naturally spread out over time, dissolving into a diffuse, invisible sheet of dust due to constant micro-collisions. However, the active presence of the tiny Shepherd satellites and the complex gravitational resonances of the inner moons keep these tracks sharply defined, locking them into place for millions of years. This ongoing battle between chaotic dispersion and orderly confinement suggests that the rings are not permanent, unchanging fixtures, but are instead dynamic, evolving systems that must be constantly maintained by the laws of physics. It invites us to view the ring system as a fleeting masterpiece of cosmic geometry, a beautiful arrangement of matter that exists precisely because the forces of gravity are perfectly balanced. As the lopsided magnetosphere tumbles through space like a lopsided top, it creates a unique wave of energy that ripples outward toward the very edge of our solar system. The planet drifts relatively close to the heliopause, the grand invisible boundary where the streaming wind from our sun finally clashes with the cold, raw environment of interstellar space. Because the ice giant's magnetic field twists and opens every 17 hours, it injects a highly irregular pulse of plasma into the outer heliosphere, altering the local cosmic weather. This lopsided energetic wake acts like a rhythmic drumbeat echoing through the outer system, a signal that can be detected by sensitive instruments traveling far beyond the planets. It highlights the profound interconnectedness of the cosmos, proving that the eccentric movements of a single tilted giant can influence the grand energetic shield that protects our entire planetary family. In evaluating the architecture of this sideways planetary kingdom, scientists often note the intriguing absence of a single, massive satellite that completely dominates the system. While Saturn possesses colossal Titan and Neptune commands the captured world of Triton, the satellite family of our aquamarine giant is remarkably balanced among its 5 major literary moons. No single moon holds a tyrannical monopoly over the local gravity, allowing Titania, Oberon, Ariel, Umbriel, and Miranda to coexist in a state of shared orbital equilibrium. This unique distribution of mass suggests that the original debris disk surrounding the tilted world was evenly sorted, preventing a single runaway moon from devouring all the available material during the formation process. It results in a highly democratic celestial neighborhood where multiple diverse worlds can develop their own unique geologies without being crushed by the presence of a giant neighbor. The ongoing refinement of planetary classification has cemented the status of this world and its neighbor Neptune as a fundamentally distinct category of celestial bodies known as ice giants. For generations, these outer worlds were casually lumped together with Jupiter and Saturn under the broad umbrella of gas giants, a classification that ignored their vastly different internal chemistries. Modern astrophysics recognizes that the deep, slushy mantle of water, ammonia, and methane sets these intermediate worlds completely apart from the true gas colossi, which are almost entirely composed of liquid hydrogen. This distinct classification helps scientists better understand the diverse mechanisms of planetary creation, proving that our solar system is organized into 3 clear zones: rocky, gaseous, and icy. By viewing the aquamarine sphere through the lens of this unique class, we gain a much deeper appreciation for the rich variety of forms that matter can assume across the infinite reaches of space. The wind patterns of this sideways spinning giant reveal another striking departure from the meteorological rules that govern the other giant planets in our system. On Jupiter, Saturn, and Neptune, the upper atmosphere is dominated by a powerful, superfast jet stream that rushes around the equator in the direction of the planet's rotation. On our lopsided world, however, the equatorial winds actually blow in a backward direction, moving counter to the planet's swift 17-hour spin, while the westward winds are concentrated near the lonely poles. This inverted wind structure is a direct consequence of the planet's lack of substantial internal heat, which prevents the formation of traditional equatorial convection currents. It stands as a fascinating atmospheric anomaly, proving that without a warm internal engine to drive the air, a world's weather will organize itself in completely unexpected ways. As we complete this stage of our deep exploration, we are left with an overriding impression of a world that has been beautifully preserved by the absolute stillness of the outer cosmic void. Cut off from the energetic warmth of the inner solar system, rolling peacefully on its side across an 84-year orbit, the planet remains a sanctuary of cold, unbothered order. Its methane clouds silently absorb the distant red starlight. Its diamond rain falls in total darkness through the superionic ocean, and its literary moons spin in their vertical tracks without a sound. This grand planetary system operates with a quiet efficiency that requires no external validation, a timeless monument to the elegant laws of gravity and motion that govern the universe. By shifting our perspective to this remote, aquamarine realm, we are reminded of the profound peace that reigns in the deep, dark spaces between the stars, where worlds drift in endless, tranquil harmony. To fully grasp how this lopsided world ended up so far in the frozen depth, we must look to modern cosmological models of early solar system migration. According to the widely accepted NICE model, the ice giants did not originally form in the remote orbits they occupy today, but were positioned much closer to the Sun, nestled between Saturn and the early Kuiper belt. Over hundreds of millions of years, gravitational interactions with chaotic swarms of planetesimals caused the giant worlds to shift their positions, triggering a grand orbital instability that pushed the ice giant violently outward. During this dramatic cosmic migration, it is highly probable that the planet swapped places with its twin Neptune, trading tracks before finally settling into its current 84-year orbit. This chaotic history reveals that the neat, orderly layout of our current solar system is the result of a violent cosmic restructuring, where entire worlds were cast out into the dark like drifting islands. Tracing the outermost boundaries of the planet's gravitational kingdom, we discover the fascinating collection of 9 irregular outer moons that circle the world at staggering distances. Unlike the inner literary satellites that orbit in the tilted equatorial plane, these remote bodies move along highly inclined, eccentric, and predominantly retrograde paths that carry them millions of kilometers out into the dark void. Satellites like Sycorax and Caliban are believed to be ancient Kuiper belt objects, or stray asteroids that wandered too close to the ice giant during its early outward migration and became permanently trapped by its gravity. Their irregular, looping tracks tell a silent story of ancient cosmic capture, representing a bridge between the planet's immediate family and the raw, unmapped territory of the outer solar system. Observing these distant wanderers reminds us that the edge of a planet's domain is not a sharp boundary, but a soft, fading transition zone where the world softly blends into the interstellar deep. In the absolute isolation of its remote orbit, the aquamarine giant acts as a massive cosmic shield, continuously interacting with high-energy galactic cosmic rays that stream in from the far corners of the galaxy. Because the planet's lopsided magnetosphere is constantly twisting and opening like a giant celestial valve, these energetic interstellar particles can penetrate deep into the upper layers of the atmosphere. This continuous subatomic bombardment breaks apart the fragile chemical bonds of the high-altitude methane, triggering the unique photochemical reactions that produce the subtle stratospheric smog of ethane and acetylene. A similar process occurs on the surfaces of the outer irregular moons and dark rings, where millions of years of radiation processing turn the primitive frozen ices into dark, complex carbon polymers. It highlights a beautiful, ongoing dialogue between the planet and the deep universe, where interstellar energy leaves a permanent physical imprint on the chemistry of an ice giant. The quiet space surrounding this pale turquoise sphere is continuously bombarded by an invisible rain of interplanetary dust and micrometeorites drifting inward from the nearby Edgeworth-Kuiper belt. As these tiny fragments of primitive rock and ice slam into the upper atmosphere at incredible velocities, they completely disintegrate, depositing trace amounts of heavy elements and water vapor into the gaseous layers. This continuous cosmic deposition provides a vital source of oxygen compounds to the high stratosphere, driving rare chemical pathways that could not otherwise exist in a hydrogen-dominated environment. The incoming dust also interacts directly with the dark charcoal rings, generating the fine, diffuse sheets of microscopic grains that slowly spiral downward toward the cloud tops. This constant exchange of matter proves that even a world so profoundly isolated is still intimately connected to the broader celestial debris field, silently absorbing the dust of ancient comets across eons of time. Reflecting deeply upon the planet's unique thermal profile, scientists continue to investigate the exact mechanisms responsible for the almost complete lack of internal heat generation. Traditional models of planetary cooling suggest that a world of this size should still retain a substantial amount of primordial warmth left over from its gravitational collapse billions of years ago. One compelling explanation proposes that the extreme stratification within the superyonic water and ammonia mantle, acts as a massive thermal blanket, completely trapping the core's heat deep inside and preventing it from rising to the surface. This unique internal barrier creates a state of deep stagnation, locking the core's energy away while leaving the upper atmosphere exposed to the absolute chill of the outer void. It reveals a planet whose interior is structurally insulated from its exterior. A silent powerhouse whose warmth is permanently buried beneath thousands of kilometers of fluid ice. While we frequently marvel at the immense depth of the aquamarine sky, the gaseous envelope of hydrogen, helium, and methane actually accounts for only a small fraction of the planet's total mass. The vast majority of the world's 14.5 Earth masses is concentrated within the deep, superpressurized liquid mantle, and the central rocky core described in our earlier explorations. The outer atmosphere represents a delicate, superficial veil, a beautiful gaseous skin wrapped tightly around a massive, churning ocean of exotic ionic fluids. This specific structural balance explains why the planet possesses such low overall density while still exerting a powerful gravitational pull on its 27 orbiting moons. It forces us to adjust our visual perspective, recognizing that the uniform blue sphere we see from afar is merely the thin, elegant mask of a deeply complex, liquid-dominated world. As the ice giant continues its slow, majestic 84-year journey through the constellations of the zodiac, it occasionally passes directly in front of bright, distant stars as viewed from our terrestrial perspective. These rare astronomical occultations offer modern scientists a priceless opportunity to study the finest details of the planet's atmosphere, and rings without the immense cost of launching a deep space probe. By measuring the precise fractions of a second it takes for a star's light to fade through the high-altitude smog, researchers can map the changing pressures and temperatures of the stratosphere across different seasons. These alignments represent a perfect union of local planetary architecture and distant galactic geometry. Using the ancient light of stars thousands of light years away to illuminate the dark pathways of our local system, they stand as a gentle reminder that every object in the night sky is part of a grand, interconnected cosmic clockwork, where patience is rewarded with deep scientific revelation. The intricate orbital relationship between the 13 dark rings and the inner literary satellites represents one of the most gravitationally crowded and delicate environments in the entire solar system. Because these small moons and dense tracts of charcoal boulders are packed tightly within a narrow region just above the upper atmosphere, their mutual gravitational tugs are constantly competing for dominance. Computer simulations of this chaotic orbital matrix suggest that the inner system is fundamentally unstable on long cosmic timescales, with orbits continuously shifting and warping over millions of years. It is highly probable that some of the smaller inner moons will eventually collide with one another, or be torn apart by the planet's immense tidal forces, creating entirely new rings in the distant future. This realization introduces a profound element of impermanence to the sideways giant, showing that the elegant geometric harmony we observe today is merely a temporary snapshot in a continuous, evolving cycle of destruction and rebirth. When astrobiologists evaluate the potential for habitability within this extreme cryogenic world, they are confronted with an environment that is profoundly hostile to the traditional mechanisms of terrestrial life. The absolute lack of a solid surface, combined with the terrifying speeds of the 900-kilometer-per-hour winds and temperatures plunging below -200 degrees, creates an insurmountable barrier for biological development in the upper atmosphere. Deeper down within the slushy mantle, while liquid water and chemical nutrients are abundant, the crushing gravitational pressures and blistering heat create an environment where complex organic molecules are instantly torn apart. Even the rain of pure diamonds falling toward the core serves as a beautiful but deadly reminder of the extreme physical forces reigning supreme beneath the quiet aquamarine sky. This world stands not as a cradle for life, but as a breathtaking monument to the non-biological complexity of the universe, a domain where chemistry and physics execute their grand designs in total, sterile perfection. The final and perhaps most profound truth regarding this sideways spinning ice giant is its role as a vital missing link in our comprehensive understanding of planetary systems across the galaxy. By challenging every conventional rule of axial tilt, magnetic geometry, and thermal behavior, this pale turquoise sphere forces humanity to abandon its terrestrial biases and expand its scientific horizons. It stands as a majestic, unbothered sentinel at the edge of our stellar neighborhood, a world that chose to move to its own unique rhythm while maintaining a state of flawless, enduring equilibrium across billions of years. Every drop of diamond rain, every lopsided swing of its magnetic shield, and every silent orbit of its literary moons adds a beautiful line to the grand story of the cosmos. As we finish our detailed tracking of its 100 distinct realities, we are left with a deep appreciation for a world that reminds us how much mystery still lingers in the quiet, icy dark. Our long, drifting journey through the remote architecture of this aquamarine world now draws to its natural, quiet conclusion, leaving us at the edge of the immense planetary system we have so carefully explored. We have witnessed the gentle history of its accidental discovery in the starry sky, and pondered the colossal ancient forces that tipped an entire planet completely onto its side. We have looked deep through the serene, methane-rich fog to visualize the chaotic storms churning in total silence, and followed the slow fall of diamond rain, moving down through the supersonic ocean toward the rocky core. The 13 narrow, charcoal pathways of the ring system spin endlessly in their razor-thin planes, guarded by tiny frozen satellites that maintain absolute geometric order against the empty void. Farther out, the 27 literary moons complete their vertical orbits like a majestic cosmic theater, completely aligned with the planet's unorthodox posture across billions of years of deep isolation. Every scientific truth we have uncovered paints a picture of a world that operates in perfect, self-contained balance, unbothered by the chaotic noise of the inner solar system. As we prepare to drift away from this beautiful ice giant, the pale turquoise disk begins to recede slowly into the background, blending seamlessly with the infinite velvet tapestry of the cosmos. The intense, lopsided magnetic field continues its complex, tumbling dance, carving its invisible corkscrew wake through the streaming solar wind in complete, undisturbed privacy. Here, billions of kilometers away from the warm heart of our stellar neighborhood, we are reminded of the profound stability that can exist within the most radical anomalies of nature. The universe does not require uniformity to maintain its grand harmony. It allows a giant world to roll backward along its 84-year track, creating a masterpiece of cryogenic physics out of absolute cold. This remote kingdom stands as a timeless testament to the beauty of the unexplored deep, a sanctuary of stillness where time moves on a scale of long planetary decades. To look upon this world is to understand that the darkness of space is not a terrifying emptiness, but a gentle, preserving embrace that cradles the grand designs of gravity and motion. Now, let the lingering images of the aquamarine clouds, the ghostly blue outer ring, and the fractured landscapes of Miranda settle softly into the quiet spaces of your own awareness. The eternal, frozen peace of the outer solar system infuses this moment with a deep sense of security, wrapping the mind in the very same stillness that preserves the ice giant across eons. We leave the lopsided world to continue its long, silent rotation through the constellations, drifting safely within the mathematical precision of its cosmic path. The chaotic details of the day fade away completely, replaced by the unhurried, rhythmic breathing of a planetary climate that has lasted for billions of years. Allow yourself to rest completely within this grand cosmic perspective, sinking deep into the comforting, unblinking silence of the limitless starry sky. Sleep peacefully now, as we leave the pale giant to its endless, quiet journey through the dark void, perfectly balanced in the timeless cradle of the infinite universe.